अब मेरी आवाज़ सुन पा रहे हैं?
Yes, sir.
Okay. So this lecture is going to be about Tonelli's theorem. In our previous lecture we learned about Fibonacci's theorem. वो अभी आपके स्क्रीन पे है. मैंने कल आपको we proved this actually. मैंने आपको दिखाया था if f is mu cross nu integrable, then both the iterated integrals of f exist. Not only they exist, they are equal, and the common value is the double integral of f. That is the Fibonacci's theorem. Tonelli's theorem, in a way, is a partial converse of the Fibonacci's theorem. I'll first give some motivation for the result. The converse of the Fibonacci's theorem, generally speaking, is not true. That is, mere existence of the iterated integrals is not sufficient for integrability. And you can see this, or you can justify whatever I am saying by means of this example. If you examine this example, which is given in 1, fx equal to this x square minus y square by x square plus y square whole square, when x is xy, where xy is coming from the rectangle, 0 1 cross 0 1, with the exception of the origin. At origin the function is defined as 0. If you examine this function f, then it turns out both the iterated integrals exist, but they are not equal. ये कल भी हमने ये example देखी थी. Although the iterated integrals, they exist. For example, the iterated integral dx dy is equal to minus pi by 4, and the iterated integral dy dx is equal to pi by 4. And I suggest you to go for the verification. Okay, so this I leave for you. You check that they are indeed the first iterated integral dx dy जो यहाँ है, which is to the left on your screen, is actually minus pi by 4, and the second is pi by 4. Now, by Fibonacci's theorem, this function f, whose iterated integrals are currently displayed on your screen, the function f, it cannot be integrable. Because if it is integrable, then by Fibonacci's theorem, the iterated integrals must be equal. Now, since the iterated integrals are not equal, so function cannot be integrable. So this is an example of a non-integrable function whose iterated integrals exist. So thereby I have actually now justified my assertion. Mere existence of iterated integrals, it does not imply integrability. Function f, this function f, is not integrable, but its iterated integrals exist. So that is the reason I said that mere existence of iterated integrals is not sufficient for integrability. You require something more actually. Now this example actually gives rise to this question. This question naturally arises when we examine the previous example. And the question is, are there any additional conditions under which the converse of the Fibonacci's theorem holds? In general, we saw that converse is not true, because existence of iterated integrals does not imply integrability. So generally speaking, converse is not true, but the question is, are there any additional conditions, condition, under which the converse of the Fibonacci's theorem holds? And the answer to this question is yes. And the answer is actually given by the Tonelli's theorem. Tonelli's theorem answers this question in affirmative. It has a positive answer to our query. Tonelli's theorem says that yes, there are additional conditions which ensure that the converse of the Fibonacci's theorem holds. Okay? And this is the statement of the Tonelli's theorem. Let x is mu, y sigma nu be two sigma finite measured spaces. So this time around we are not dealing with arbitrary measured spaces. The two measured spaces, x is mu and y sigma nu, they must be sigma finite measured spaces. And let this be their product measure space x cross y SO times sigma mu cross nu. It's the product space of these two sigma finite measure spaces. Next, we are assuming that f is a function whose domain is x cross y, Cartesian product of x and y, and it takes values in 0 infinity. So that means this f is a non-negative function. And in addition to this non-negativity, we are also assuming that it's a measurable function. वही मैं यहाँ लिख रहा हूँ. Assume f from x cross y into 0 infinity is a non-negative measurable function. So the function has to be non-negative and measurable. और इसके बाद, if one of the iterated integrals exist, there are two iterated integrals because this f is a function of two variables, and my assumption is, my requirement is, one of those, only one of those should exist. मुझे दोनों की existence नहीं चाहिए, मुझे बस एक की existence चाहिए. If one of the iterated integrals of f exist, then the theorem guarantees that f is integrable. Now that if f is integrable, so we can use Tonelli's theorem. Tonelli's theorem guarantees both the iterated integrals. मैं पता नहीं क्या कह रहा हूँ. We can use Fibonacci's theorem, right? Basically ये ऐसे है. Under these conditions, if x is mu and y sigma nu be sigma finite measure spaces and this be a product space, and if f is non-negative measurable function, and if one of the iterated integrals of f exist, then Tonelli's theorem guarantees that f is mu cross nu integrable. This is guaranteed by the Tonelli's theorem. F is mu cross nu integrable. Now f is mu cross nu integrable, we can apply here Fibonacci's theorem. ये मैं असल में आपसे कह रहा था. F is mu cross nu integrable, so I can use Fibonacci's theorem, and Fibonacci's theorem will guarantee that both the iterated integrals exist. We have started with the assumption that one of the iterated integrals exist. One of the iterated integrals exist. But after this stage, since now we can use the Fibonacci's theorem, we can conclude both the iterated integrals exist. So if you incorporate the information which this Fibonacci's theorem now offers, now you can conclude that the other iterated integral also exists. And the three integrals, the two iterated integrals and the double integral of f, they will be all equal. This is the Tonelli's theorem. उसको ठीक से देख लीजिए. अब जो एडिशनल रिक्वायरमेंट्स है, वो एडिशनल कंडीशंस है, वो क्या है यहाँ पे? पहले तो वो दो जो मेजर स्पेसेस है आपकी, जिनसे आप वो प्रोडक्ट स्पेस क्रिएट करते हैं, दे मस्ट बी सिग्मा फाइनाइट स्पेसेस. ठीक, तो ये एक एडिशनल कंडीशन है, बिकॉज अदरवाइज वी डोंट रिक्वायर सिग्मा फाइनाइटनेस. यहाँ आपको चाहिए ये. एक और एडिशनल कंडीशन है ये नॉन नेगेटिविटी. एफ जो है, इट हैज़ टू बी अ नॉन नेगेटिव मेजरेबल फंक्शन. मेजरेबिलिटी तो समझ आता है, बट नॉन नेगेटिविटी जो है ना, दिस इज एन एडिशनल कंडीशन. ठीक है. इफ अगर ये सारी चीज़ें हो रही है, देन एग्जिस्टेंस ऑफ वन ऑफ द इटरेटेड इंटीग्रल्स actually guarantees existence of the other. In fact, it actually guarantees integrability of the function. And once the function is integrable by Fibonacci's theorem, the other iterated integral must exist, and the two iterated integrals and the double integral of f, they must be all equal, again by Fibonacci's theorem. So this is Tonelli's theorem. Now we'll prove this, and to prove this theorem we'll be requiring certain results. These are not some well-known results. These are not वो results नहीं है which we use frequently. So that is that. हालांकि they are simple results, कोई उतना ज़्यादा नहीं है. But since they are not used that frequently, so I have listed these results which I'll use in the proof as lemmas. ठीक है? This is lemma 1, and it's an assignment for you. ये इसका proof मैं आपको नहीं दिखाऊंगा, because it just no, uses the definition. आपको definition के अलावा ज़्यादा कुछ नहीं करना है. इसका statement ये है, let x is mu, y sigma nu be two sigma finite measure spaces, and x cross y SO times sigma mu cross nu be their product space, then this is the conclusion now. There exists an increasing sequence En and running from 1 to infinity of mu cross nu measurable subsets of x cross y with union of Ens equal to x cross y, and the outer measure of each En will be less than infinity. Now अगर आप ये इसको ठीक से एग्जामिन करेंगे conclusion को, it says that there exists a sequence En whose union is x and outer measure of each En is less than infinity. So this actually is the definition of sigma finiteness. So consequently, this lemma also tells us that the product space of two sigma finite spaces is again a sigma finite space. समझ रहे हैं आप? मतलब if you take two sigma finite spaces, their product space is again a sigma finite space. So it's an exercise for you. ये आप try करेंगे, and you have to just use the definition. You have to use the definition of sigma finiteness. और दूसरी लेमा जो हम इस्तेमाल करेंगे, it will be the approximation lemma. ये मैंने आपको वो इससे पहले जो हमारा मेजर थ्योरी का जो कोर्स था सेकंड सेम वाला, उसमें मैंने इसका आपको प्रूफ दिखाया. I have proved this result there. It states that if you have a measure space and f a non-negative measurable function, then there exists a sequence phi n of non-negative simple functions such that these phi n's will be increasing. Phi n x will be less than or equal to phi n plus 1x, and this will be true for all x's and for all n's. Means phi n's are increasing and phi n's are converging pointwise to f for all x's and x. This is the approximation lemma. Besides these two lemmas, we'll be also using the dominated convergence theorem. But since dominated convergence theorem is frequently used result, so I won't be using, or I won't be listing DCT as a lemma here, because we use DCT frequently. Okay? So these are the two lemmas. Now we come to the proof. I'll directly begin with the proof. मेरे ख्याल से आपने ये चीज़ कॉपी करी होगी. This is the Tonelli's theorem. If you insist, I can take a screen clipping of this. इतना मैं कर सकता हूँ. इतना मैं वो बेहतर होगा मेरे ख्याल से. I'll take a screen clipping of this. This is the statement which we are going to prove, and I'll also, I think I should now borrow those lemmas also. This is lemma 1, no? No, sorry, ठीक से नहीं आएगा यहाँ. पूरी इंफॉर्मेशन नहीं आ रही थी इसमें. Proof of lemma 2 I have already given you in the second semester. Lemma 1 is an exercise for you. The proof of the lemma 1 is an exercise. So I'll start with the proof of the main theorem. Proof of the main theorem. And you can see that both the lemmas are readily applicable. ठीक है ना, मतलब you don't need to make any preparations for the lemmas. The lemmas are readily applicable. जैसे lemma 1, इसके लिए आपको अब इसकी रिक्वायरमेंट है you must have 2 sigma finite measure spaces, और वो है हमारे स्टेटमेंट में. हाँ, lemma 2 में आपको एक थोड़ी सी स्लाइट एडजस्टमेंट करनी होगी. इसका जो आइडिया है ना उसे आपने कैप्चर करना है, not exactly the words. You have to capture the idea only from lemma 2. And the idea is this: if you have possess a non-negative measurable function, then there is a sequence of non-negative simple functions which increase and eventually converge to the non-negative measurable function. अब when you use lemma 2, आप किसे use करेंगे as non-negative measurable function? Obviously you'll use f, because f is a non-negative measurable function, but this f is defined on the product space. So this is the adjustment which I was talking about. You have to basically use this lemma 2 on the product space. Don't go by these symbols excess mu. ये बस आइडिया आपको यहाँ से ना बोरो कर रहे हैं, एंड अदरवाइज इसको जो अप्लाई है वो आपको करना है ऑन द प्रोडक्ट स्पेस, बिकॉज जो नॉन नेगेटिव मेजरेबल फंक्शन हमें दिया गया है, इट इज़ डिफाइंड ओवर द प्रोडक्ट स्पेस. आई विल बिगिन विद द प्रूफ. फर्स्ट विल डायरेक्टली यूज लेमा 1. ठीक है, by lemma 1 we can find क्या कर सकते हैं, we can find an increasing sequence. lemma 1 is readily applicable, उसमें कोई एडजस्टमेंट भी नहीं करनी है, कोई मॉडरेशन की ज़रूरत है. ठीक है, so by lemma 1 we can find an increasing sequence En of mu cross nu measurable subsets of x cross y with union equal to x cross y, and outer measure of each En will be finite. मैं ये सारी चीज़ें लिख रहा हूँ. We can find an increasing sequence. Find an increasing sequence this En running from 1 to infinity of mu cross nu measurable subsets of x Cartesian product y such that union of these Ens running from 1 to infinity. और हाँ, यहाँ मैं थोड़ा सा इसको अभी जो है ना आप देखिए फिर आप लिखेंगे, such that union of all the Ens, जिसको मैं ऐसे लिख सकता हूँ, union I running from 1 to infinity ei. Lemma 1 guarantees that union of all these sets in this sequence will be x Cartesian product y. ठीक है, और ये जो है इसको मैं थोड़ा सा यहाँ ना, eventually I'll be using this, so that is the reason मैं पहले ये preparation कर रहा हूँ. यहाँ इसको मैं ऐसे लिख सकता हूँ, I can write this as limit n goes to infinity union I runs from 1 to n e sub I. लिख सकते हैं ना ऐसे. ठीक. Now what is union I runs from 1 to n ei? We know that these ei's, they are increasing, so the union I running from 1 to n ei will be actually en. So this is actually इसको ऐसे लिख सकता हूँ, लिमिट n goes to infinity en is equal to x cross y. So basically these ens are growing to x cross y. This is the idea which I want to communicate. Ens are increasing, union is x cross y. So basically it means that ens are growing to x cross y. वही मैंने यहाँ ना लिखा है, इसको थोड़ा ठीक से लिखेंगे क्योंकि ये कुछ मेसी लग रहा है मुझे. Such that असल में ये है en जो है, it will be limit limit n goes to infinity en. This is same as limit n goes to infinity union I runs from 1 to n ei, because union I runs from 1 to n. Ei is actually en because ens are increasing, and this is I runs from 1 to n, n goes infinity, so this is I runs from 1 to infinity ei, which is x cross y. ठीक है, such that this, और हाँ इसमें वो भी है, outer measures are finite, and mu cross nu star of these ens, they are finite quantities less than infinity, and they are finite for all the n's in the set of natural numbers. So this is what lemma 1 is offering us. I got this by using lemma 1. Okay, next I'll use lemma 2. Also by lemma 2 क्या होगा, we can find what? We can find an increasing sequence, and increasing sequence phi n running from 1 to infinity of what? Of non-negative simple functions. और ये सिंपल फंक्शन जो होंगे, दे विल बी सिंपल ओवर द प्रोडक्ट स्पेस. वो पहले मैं आपको बता चुका हूँ. सिंपल फंक्शंस ओवर द प्रोडक्ट स्पेस विच इज x क्रॉस y s o टाइम्स सिग्मा mu क्रॉस nu. Or the product space, this, such that limit n goes infinity phi n x comma y, this will be equal, because they will be going to f, these phi n's will be equal to f of x comma y, and this will be true for all x's and y's, मतलब ordered pairs in the Cartesian product in x cross y. ठीक है? Now, as of now, these phi n's are of no use to us because they are only simple functions. We cannot handle them, these simple functions, because a simple function need not be integrable. What we try to do now, we'll create step functions using these simple functions. ठीक है, और सिंपल को हम इंटीग्रेट नहीं कर सकते, मुझे कुछ हम मॉडिफिकेशन या मुझे कुछ एडजस्टमेंट, इट्स नेसेसरी टू मेक सम एडजस्टमेंट्स, और मैं अब वही कर रहा हूँ. इसके लिए आप ऐसे करेंगे, फॉर ईच n in the set of natural numbers will define something. And there is a necessity of defining this. जो मैं आपसे पहले ही कह रहा हूँ कि these phi n's are of no use to us actually. Now, honestly speaking, I cannot handle phi n's because they are only simple functions. I cannot integrate them. We can integrate stub functions. So that means we somehow need to create stub functions out of these simple functions. और मैं वही अब करने जा रहा हूँ. Define gamma n. और ये gamma n मैं कैसे define करूँगा? I'll define gamma n as, एक तो यही phi n लेंगे और इसको multiply करेंगे with the characteristic function of en, where this en, rather I should say where these ens are these ens, the terms of the sequence. So for each n we are doing this. Now what can you tell me about this gamma n? वही कलर इस्तेमाल करेंगे फिलहाल. Then gamma n running from 1 to infinity. Obviously we'll get a sequence of these gamma, because for each n we are defining a gamma n. So we'll get a sequence of these gamma n's, and this sequence of gamma n's is, मैं इसकी अब कुछ इसकी properties list कर रहा हूँ, and you have to verify each property, is an increasing sequence. बताइए क्यों है ये increasing? इसका रीज़न ये है, phi n's are increasing and chi e n's are also increasing. Why these chi e n's are increasing? Well, इसका ये आंसर है actually, because e n's are increasing. That means e n is contained in e n plus 1, and that is the reason chi e n will be less than or equal characteristic function of e n plus 1, right? And phi n's के बारे में हमें पता ही है, बिकॉज जो phi n's जहाँ से आ रहा है वो अप्रोक्सीमेशन लेमा से आ रहा है, और अप्रोक्सीमेशन लेमा ही हमें गारंटी देती है कि दैट phi n's आर इंक्रीजिंग. phi n's भी इंक्रीज हो रहा है और ये chi e n's भी. You simply multiply this and this, left side with left side, right side with right side, left side with left side, and right side with right side. यहाँ से जब आप मल्टीप्लाई करेंगे you'll get gamma n, और यहाँ से जब मल्टीप्लाई करेंगे राइट साइड्स को you'll get gamma n plus 1. So gamma n is less or equal to gamma n plus 1, so gamma n's are increasing. So this is an increasing sequence of, increasing justify हो गया, of non-negative. और मुझे नहीं लगता कि इसकी कोई elaboration चाहिए आपको non-negativity की, because phi n and chi n's, they are non-negative, so the product will be non-negative. So gamma n's are non-negative. Of non-negative, अब इसमें और भी है, non-negative stub functions. Gamma n's, they are stub functions. बताइए कैसे? मैं बाकी डिटेल्स रब कर रहा हूँ. कोई बता सकता है आप में से how these gamma n's are stub functions? Well, इसका सिंपल रीज़न ये है, आउटसाइड ई एन, बिकॉज यहाँ कैरेक्टरिस्टिक फंक्शन आप देख रहे हैं, सो gamma n जो है इट विल बी ज़ीरो आउटसाइड, सॉरी आउटसाइड ई एन है ना, बिकॉज कैरेक्टरिस्टिक फंक्शन इन्वॉल्व हो रहा है वहाँ ई एन का. सो ई एन के बाहर gamma n विल बी ज़ीरो. What is En? En is a set of finite outer measure. So that means gamma n's, they vanish outside a set of finite outer measure. और यहाँ से these gamma n's, they take only finitely many values because they are simple functions. Phi n is a simple function, chi n is a simple function, chi e n is a simple function, product of two simple functions is a simple function. So this is a simple function. So gamma n is a simple function and it vanishes outside En. En is a set of finite outer measure. So gamma n is a simple function which vanishes outside a set of finite outer measure. So that means gamma n is a stub function. So we have created a sequence of stub functions now, and we can work with this now. इनको अब handle हम कर सकते हैं. This is an increasing sequence of stub functions. इसी में हम भी लिखेंगे with I want to examine the limit of these gamma n's. I want to examine limit n goes to infinity gamma n x comma y. So what will be this limit n goes to infinity? ऐसे रहेगा. Gamma n is phi n times this, so gamma n x comma evaluated at x comma y will be phi n evaluated at x comma y times characteristic function of en evaluated at x comma y. ठीक है. Now we have to take the limit as n goes to infinity, और इसके लिए आप वो ऊपर वाली इंफॉर्मेशन इस्तेमाल करेंगे. ens के बारे में मुझे पता है कि that in the limit ens become x cross y, they grow to x cross y. So in the limit this characteristic function is growing to the characteristic function of x cross y, and characteristic function of x cross y is 1. So in the limit this thing becomes 1. What about this? What about phi n in the limit? Well, उसके लिए भी हमारे पास information है, वो ये है. In the limit phi n's become f. So in the limit it becomes f times 1, which is f. So this is equal to f of x comma y. And this is true for which x's and y's? The answer is for all x's and y's. For all ordered pairs x comma y in the Cartesian product. Full stop. ठीक है. So effectively I have created, अगर देखा जाए, using the sequence phi n I created another sequence gamma n. और अगर properties को आप compare करेंगे, phi n is an increasing sequence of non-negative functions, gamma n भी वही है. It's an increasing sequence of non-negative functions. Phi n converge to f, gamma n also converge to f pointwise. तो gamma n में वो सारी properties है जो phi n में है, और gamma n में एक additional property भी है, that these gamma n's are step functions. तो basically ये करने का जो intention है वो ये है कि मैं जो है ना वो एक improved sequence चाहता था. phi n's को मैं handle नहीं कर सकता था, I cannot integrate them, but now these gamma n's I can handle and I can integrate them, and I can use all the integration related results. This is actually the reason of creating these gamma n's. अब एक और चीज़ आप देखिए, since these gamma n's n in the set of natural numbers, they are step, we know that they are step, so therefore they are integrable also, because every step function is integrable, are step, and therefore integrable. Functions. And gamma n's are defined over x cross y, so they are integrable functions over the product measure space. Integrable functions over product space x cross x Cartesian product y s o times sigma mu cross nu. Okay, so these are step and therefore integrable functions over this. अब यहाँ हम क्या करेंगे? We'll make use of the Fibonacci theorem, comma, it follows Fibonacci theorem is applicable because Fibonacci theorem के लिए बस आपको integrability चाहिए. You require only mu cross nu integrability. वो है in gamma n's में. So it follows by the Fibonacci theorem that the iterated integrals of these gamma n's, और वो ये होंगे integral over x, integral over y, gamma n d nu d mu, and integral over y, integral over x, gamma n d mu d nu. These iterated integrals would exist, and they would exist for all the n's, for all n's in the set of natural numbers, because every gamma n is integrable. So that is the reason each of these iterated integrals would exist. Full stop. ठीक है? Now I'll make use of the condition, my assumption. What we are assuming that one of the iterated integrals of f exist. वो कोई भी सा हो सकता है. f के दो iterated integrals है, दो में से कोई भी exist हो सकता है. We'll assume that the iterated integral over x, integral over y, that means d nu d mu वाला जो iterated integral है, we'll assume कि that exists. ठीक है, तो बेसिकली दो में से किसी एक ही एग्जिस्टेंस एज्यूम करिए. मैं वो दूसरे वाले की एग्जिस्टेंस, मतलब नेचुरली जो है ना वही है, इंटीग्रल ओवर एक्स, इंटीग्रल ओवर वाई, डी न्यू डी म्यू, मैं उसकी एग्जिस्टेंस एज्यूम कर रहा हूँ. Assume that because I know that one of the two exists, so I am assuming this exists. Integral over x, integral over y, f d nu d mu exists. ये एग्जिस्ट हो रहा है. ठीक है, अब हम पता है क्या करेंगे इसके बाद. We'll use this assumption that this exists together with the existence of these iterated integrals. हम यही अब परस्यू करेंगे, वो अब देखेंगे कैसे. अब यहाँ कुछ टेक्निकलिटीज़ मैं ना एड्रेस कर रहा हूँ. लेट ए नॉट बी इक्वल, ये ध्यान से देखिएगा, ए नॉट इज गोइंग टू बी द सेट ऑफ ऑल दोज एक्सेस इन एक्स such that f is a function of two variables. मैं आपसे यहाँ क्या कर रहा हूँ, you fix the first variable at x, so it becomes a function of the second variable. ठीक है, now it's a function of the second variable. Now this function, which is basically function of second variable, it may or may not be integrable. It may or may not be new integrable. ठीक है, ये हो भी सकता है और नहीं भी हो सकता है. Now if it is not new integrable, अगर ये नहीं है new integrable, we'll collect that x in a naught. So a naught is going to be set of those x's in x such that this is not a new integrable function. This will be a naught. अभी हम इसमें कुछ और चीज़ें भी define कर रहे हैं, comma. Next I'll define a n. And this n will be coming from the set of natural numbers. और ये an क्या होगा? This will be defined as, again this will be set of all those x's in x such that, now this time around I'll be taking gamma n, और फिर से वही करेंगे. gamma n is a function of two variables. हम क्या करेंगे, पहले variable को fix करेंगे at x, so it becomes function of the second variable. मतलब it becomes function defined on y. So it may or may not be, हो भी सकता है new integrable और नहीं भी हो सकता. If it is not new integrable, we'll collect that x in an. So an is those x's in x such that gamma n x comma dot. Gamma n x comma dot basically means you are fixing the first variable in gamma n at x and you are letting loose the second variable. Is not a new integrable function. ये होंगे ए एन्स फॉर एन इन द सेट ऑफ नेचुरल नंबर्स। यहाँ से आपको A1 मिलेगा व्हेन n is 1, फिर A2, A3 एंड सो ऑन। और इसके बाद हम एक और चीज़ डिफाइन कर रहे हैं, एंड I'll also define A. And what is this A? A is going to be the union of all these sets. So it's going to be union n running from 0 to infinity A sub n. So this will be A. ठीक है? Now, can you tell me anything about this A? आप क्या करिए, ये इन्फॉर्मेशन, ये जो यहाँ ये इन्फॉर्मेशन है अबाउट द एग्जिस्टेंस ऑफ दीज इटरेटेड इंटीग्रल्स, यू कॉल इट फर्स्ट, ठीक है? और ये जो एजम्पशन वाली इन्फॉर्मेशन है, वी आर अज्यूमिंग दिस इटरेटेड इंटीग्रल एग्जिस्ट्स, यू कॉल इट सेकंड. Now you examine first and second and try to come up with something about this A. देखिए, फॉर एग्जाम्पल मैं थोड़ी सी मदद आपकी कर रहा हूँ. यू एग्जामिन सेकेंड स्टेटमेंट. सेकेंड में आप क्या करें, आप कह रहे हैं कि दिस इज इंटीग्रेबल, या सॉरी आई शुड से दिस एग्जिस्ट्स, दिस इटरेटेड इंटीग्रल एग्जिस्ट्स. यही आप कह रहे हैं ना सेकेंड में. नाउ दिस एग्जिस्ट्स, इट मीन्स व्हाट? It means first you can integrate f with respect to the second variable. ठीक, and if you go by, if you take a look at the definition of these iterated integrals, from the definition you can now conclude that this f, it will be an integrable function of the second variable for almost all values of the first variable. For almost all values of the first variable means that measure of A naught has to be 0. And similarly, by examining statement first, you can conclude that mu measure of these ANs is 0. ठीक? Now A is the union of these null sets, so then measure of A has to be 0. मैं ये लिख रहा हूँ, in view of to decide that measure of A is 0, we are actually using first and second. In view of first and second, we conclude that mu star A is a subset of X, तो इसलिए mu star इस्तेमाल कर रहा मैं, is equal to 0. ठीक है? अब हम क्या करेंगे, I'll take an X outside A. Now for X not in A, outside A, अगर आप इसे देखेंगे X outside A, comma, if you examine this, sorry, gamma n ठीक लिखा है मैंने, हाँ ठीक है. For X is outside A, if you examine this sequence gamma n, X dot n running from 1 to infinity, X is not coming from A, so that means X is not coming from these ANs. Not coming from AN means what? अगर AN से होता, then this is not integrable. Now it is not coming from AN, means this is integrable. That means this is a sequence of integrable functions. अब ये sequence को आप कैसे basically obtain कर रहे हैं? You are obtaining this sequence of integrable functions by using gamma n's. You are fixing the first variable and gamma n's at X. अब gamma n में जो प्रॉपर्टीज़ है वो इसमें भी रिफ्लेक्ट होगी. फॉर एग्जांपल gamma n इज अ सीक्वेंस ऑफ नॉन नेगेटिव फंक्शंस, वो यहाँ भी रिफ्लेक्ट होगी, क्योंकि आफ्टर ऑल ये gamma n से ही डिराइव हो रही है ना ये सीक्वेंस. gamma n's आर इंक्रीजिंग, ये भी इंक्रीज होगी. ठीक है, तो यही चीज़ें मैं लिख रहा हूँ. फॉर x नॉट इन A, दिस is an increasing sequence of non-negative integrable functions. और यहाँ इंटीग्रेबिलिटी कौन सी इंटीग्रेबिलिटी होगी? इट विल बी न्यू इंटीग्रेबिलिटी. मैं ये लिख रहा हूँ, नॉन नेगेटिव इंक्रीजिंग सीक्वेंस ऑफ नॉन नेगेटिव न्यू इंटीग्रेबल फंक्शंस, because you have fixed the first variable, so it will be function of second variable, means function over y. So यहाँ integrability जो है it will be new integrability, because y पे जो measure है that's new integrable functions Now what happens to these functions in the limit? वो इंफॉर्मेशन हमारे पास है. What will become of these functions जो ये sequence में आप देख रहे हैं if you take the limit? If you take the limit means you are doing this limit n goes infinity gamma n x dot, और वो हमारे पास information available है. ये क्या होगा? ये देखिए, limit n goes infinity gamma n xy is equal to fxy, and this is true for all the x's and all the y's. So in particular it will be true for this fixed x also जो हम अभी a से बाहर ले रहे हैं. So therefore it will be equal to what? It will be equal to f x dot, because we don't control the second variable, we are only controlling the first variable, इसीलिए वहाँ dot है, वहाँ कुछ भी हो सकता है. So this will be the limit. So these gamma n's are going to this. Now what I know about this, since x जो है वो a से नहीं आ रहा है, और a से नहीं आने का मतलब है कि वो a naught से भी नहीं आ रहा होगा, because a में a naught भी आता है, और a naught में आने का a naught में नहीं आने का मतलब है कि that this is an integrable function. Because अगर a naught में होता then this would not have been a mu integrable function. Now since x is not an a, so therefore not an a naught, so therefore this is a new integrable function. ठीक है, मैं यही लिख रहा हूँ. These functions in this sequence, they are converging pointwise to fx dot, and fx dot is new integrable. Converging pointwise तो और जो f x dot जो है ना वो आप f से derive कर रहे हैं. f is non-negative, तो f x dot is also non-negative. Converging pointwise to a non-negative new integrable function rather you should write to the, okay, this is definite here, to the new integrable function, non-negative new integrable function, this f x dot. Full stop. अब पता है यहाँ आप DCT अप्लाई कर सकते हैं. You can use dominated convergence theorem. ठीक है, मैं क्विकली आपको ये बता रहा हूँ कि हाउ यू कैन यूज़ DCT. ये जो फंक्शंस है gamma n x dot, they are non-negative, so modulus of gamma n is same as gamma n x dot because they are non-negative. ठीक है. Now the limit is f and they are increasing, और हमें पता है कि when the functions are increasing and then and when they have a limit, the limit actually becomes the sup. So this f will be actually the sup of these gamma n's. So every gamma n will be less or equal to f x dot. So basically अब मैं आपको दिखा रहा हूँ that the modulus of each term in this sequence of integrable functions is dominated by fx dot, and about this fx dot we know that it is new integrable. ठीक है, सो यह डोमिनेशन हो रही है और पॉइंट वाइज कन्वर्जेंस भी है, वो हमने रिकॉर्ड करी है यहाँ प्रूफ में. सो वी कैन यूज DCT. Therefore, by the dominated convergence theorem, क्या होगा अब? DCT will offer basically two things. पहली चीज, the point-wise limit function is integrable. We already know that because the point-wise limit function is fx dot. So that's not a new information. हमारे नई information वो है कि we can take the limit outside the integral. ठीक है, तो DCT will guarantee that integral over y is the, because we are using new integrability. That is the reason I am taking integral over y. F x dot d nu, which in the first place can be written as integral over y because f is the limit of gamma n. So I can write this as limit n goes to infinity, gamma n x dot d nu. Now using DCT I can take this limit outside the integral. So this will be limit n goes to infinity, integral over y, gamma n x dot d nu. And this is true for which x's? The answer is for x's not in A. For all x's not in A. Now what about x's in A? We don't care because A has measure 0. मैं यही लिख रहा हूँ, that is integral over y f x dot d nu. This is equal to limit n goes to infinity, integral over y, gamma n x dot d nu, and this is true for mu almost all x's. This is true for all the x's in A. For all the x's outside A. Inside A, this may or may not be true, but since A has measure 0, so I can say that this is equal to this for mu almost all x's in X. ठीक है, this gives that, यहाँ से हमें ये भी मिलेगा, this gives that, और इसका आंसर मैं आपसे जानना चाहूँगा, इंटीग्रल ओवर y gamma n x dot d nu. This will be less than or equal integral over y f x dot d nu, and this will be true for all n's in the set of natural numbers and for mu almost all x's in X. बताइए क्यों? The reason is this, gamma n's are increasing, so integral, using the monotonicity of the integrals, integral gamma n's will also increase, and the limit of the integral gamma n's is this. So this integral happens to be, because ये अब आ रही है ना increasing sequence के limit. Increasing sequence की limit असल में sup होती है, supremum. So this integral f x d nu will actually be what? It will be sup of these integrals. That is the reason each of these integrals will be less or equal to this. और ये मैं ये क्यों लिख रहा हूँ for mu almost x's, because the limit is equal to this for mu almost all x's. So this will be sup for mu almost all x's. तो वो यहाँ आ रहा है. ठीक. अब मैं इसकी ना कुछ ये फाइनल लाइंस लिख रहा हूँ प्रूफ की. You call this, आप कोई लेबल इसको दीजिएगा. You call it 3. हमने फर्स्ट सेकंड रखा है और 3 नहीं रखा है अभी. अगर नहीं रखा है तो you call it 3, right? Call it 3. अब फिर से आप फर्स्ट एंड सेकंड को एग्जामिन करिए. पहले फर्स्ट को देखते हैं हम. इन फर्स्ट वी आर सेइंग दैट द इटरेटेड इंटीग्रल्स एग्जिस्ट. इटरेटेड इंटीग्रल्स एग्जिस्ट मीन्स ये इंटीग्रल को दोबारा इंटीग्रेट किया जा सकता है विद रिस्पेक्ट टू म्यू. दैट मीन्स दीज इंटीग्रल्स आर म्यू इंटीग्रेबल. तभी तो इटरेटेड इंटीग्रल एग्जिस्ट करेगा ना. मतलब अंदर वाले इंटीग्रल को आप फिर से इंटीग्रेट कर सकते हैं विद रिस्पेक्ट टू म्यू. सो दीज इंटीग्रल्स आर म्यू इंटीग्रेबल. दैट मीन्स दीज आर म्यू इंटीग्रेबल. ये जो यहाँ ये जो है ना, दीज आर ऑल म्यू इंटीग्रेबल, बिकॉज बाहर से एक और इंटीग्रल लगाया जा सकता है. लाइकवाइज जब आप सेकेंड को एग्जामिन करेंगे, सेकेंड से इज दिस इटरेटेड इंटीग्रल एग्जिस्ट्स. सो दैट मीन्स ये इंटीग्रल को फिर से दोबारा इंटीग्रेट किया जा सकता है विद रिस्पेक्ट टू म्यू. सो दैट मीन्स दिस इंटीग्रल इज अ म्यू इंटीग्रेबल फंक्शन. ठीक है, मैं यही चीज़ें लिख रहा हूँ. फ्रॉम फर्स्ट, पहले फर्स्ट का इस्तेमाल करेंगे. इफ़ यू टेक दीज इंटीग्रल्स, इंटीग्रल ओवर वाई गैमा एन, मैं वो एक्स नहीं लिखना चाहता हूँ, ऐसा डायरेक्टली लिखूंगा गैमा एन डी न्यू. गैमा एन डी न्यू मीन्स वी आर फिक्सिंग द फर्स्ट वेरिएबल बिकॉज यू आर ओनली इंटीग्रेटिंग विद रिस्पेक्ट टू द सेकंड वेरिएबल. एंड रनिंग फ्रॉम 1 टू इन्फिनिटी. फर्स्ट को जब आप देखेंगे आप उसको बाहर से इंटीग्रेट और कर सकते हैं विद रिस्पेक्ट टू म्यू. सो दैट मीन्स दीज आर mu integrable functions. This is a sequence of mu integrable functions. Sequence of mu integrable functions. Full stop. और हाँ, आप बेहतर है आप इसको भी कोई लेबल दीजिएगा. लेबल इसको भी दीजिएगा आप. वहाँ मैंने ऑलरेडी 3 इस्तेमाल किया तो पीछे नहीं जा सकता, तो इसको आप स्टार कहिए. अब हम क्या करेंगे, आई डायरेक्टली यूज नाउ in view of, एक तो हम स्टार का इस्तेमाल करेंगे. मैं वो DCT ऑर्डरिंग मैं इसको लिख रहा हूँ बिकॉज नाउ आई एम एक्चुअली गोइंग टू अगेन यूज द DCT. DCT रिक्वायरमेंट जिस ऑर्डर में आती है ना, वो उन्हीं ऑर्डरिंग में यहाँ लिखूँगा. नाउ इन व्यू ऑफ DCT के लिए सबसे पहले मुझे चाहिए डोमिनेशन. वो डोमिनेशन कहाँ हो रही है, वो 3 में हो रही है. अब देखिए ये जो सीक्वेंस है ऑफ म्यू इंटीग्रेबल फंक्शंस, ईच टर्म इन द सीक्वेंस इज डोमिनेटेड बाय दिस इंटीग्रल, एंड दिस इंटीग्रल फ्रॉम सेकंड वी नो दैट इज इटसेल्फ इंटीग्रेबल. ठीक. और ये जो सीक्वेंस है ऑफ दीज इंटीग्रल्स, द सीक्वेंस इज converging pointwise to this. So pointwise convergence भी है, integrability भी है, domination भी है. So therefore we can use the DCT. In view of requirements, आप ये चीज़ें ना एग्जामिन करके देख सकते हैं कि requirements are indeed fulfilled. In view of एक तो हम 3 इस्तेमाल करेंगे. 3 में domination है. फिर second इस्तेमाल करेंगे. Second says that the function which is dominating these functions is integrable. और फिर उसके बाद स्टार इस्तेमाल करेंगे. और तो मैं यहाँ लिखूँगा एंड, बिकॉज स्टार जो है ना, इट गारंटीज द पॉइंट वाइज कन्वर्जेंस जो वहाँ चाहिए होती है DCT में. इन व्यू ऑफ 3 सेकंड एंड स्टार, कॉमा by using, अब हम DCT इस्तेमाल कर रहे हैं. DCT is applicable, it is because of these three conditions. Using DCT, dominated convergence theorem, we conclude that what, बताइए. DCT will guarantee that if you take the integral of the limit of these integrable functions, that means if you take this, if you take integral over, they are mu integrable, so that means that is the reason I am taking integral over x limit n goes to infinity, integral of the limit of these mu integrable functions, और इनकी लिमिट ये होगी limit integral over y, because these functions are themselves integrals, that is the reason it will be limit of the integral gamma n d nu, तो ये होगी limit of these integrable functions और बाहर से integral, so this is integral of the limit of these integrable functions, और हाँ चूँकि ये बाहर से जो integral है it's over x, so I must write d mu here. DCT will guarantee that you can take this limit outside this integral, so this will be equal you can take this outside, ठीक है, so this will be equal to limit n goes to infinity integral over x integral over y gamma n d nu d mu फुल स्टॉप, ठीक है. तो ये मिलेगा आपको जब आप DCT इस्तेमाल करेंगे. अब इसी को हम फिर से परस्यू करेंगे, दैट इज़, अब अगर लिख रहे तो पहले वेट करिएगा फिर लिखेंगे. पहले मैं ये साइड को ले रहा हूँ, बीच में इक्वालिटी है था, तो लिमिट n goes to infinity integral over x integral over y gamma n d nu d mu. Now if I ask you what is this object, well this is an iterated integral of gamma n. What is gamma n? Gamma n is an integrable function because they are step functions, so that means ये जो iterated integral है it will be same as the double integral of gamma n. So I can write this iterated integral as the double integral also. बाहर से limit है तो वो ऐसी रहेगी, but ये है कि since these iterated integrals are same as the double integrals, so I can replace these iterated integrals by double integrals. और मैं वही कर रहा हूँ, बाहर से limit रहेगी, limit n goes to infinity integral over double integral means integral over x cross y gamma n d mu cross nu, ठीक है. So it will be equal to this, और ये जो है this, from this we know that it's also equal to this, तो आप इसको पहले लिखिए, this is equal integral over x limit n goes to infinity integral over y integral over y gamma n d nu d mu gamma n d nu, and then we'll have d mu also, d mu, ठीक है. अब ये जो लिमिट है ना, इसके बारे में मेरे पास इंफॉर्मेशन अवेलेबल है. जब मैंने वो पहली बार DCT अप्लाई करी थी, पहली बार जब मैंने DCT अप्लाई करी थी मुझे तब मिला था दैट दिस लिमिट इंटीग्रल over y gamma n d nu in the limit is equal to this, ठीक है. So I can replace this limit जो नीचे आप देख रहे हैं by this integral. And what is this? This is integral over y f d nu. इंटीग्रेटिंग विद रेस्पेक्ट टू द सेकंड वेरिएबल, और यही मैं कर रहा हूँ। बाहर वाला इंटीग्रल ऐसे ही, इंटीग्रल ओवर एक्स, और ये लिमिट जो है इसकी जगह आएगा इंटीग्रल ओवर वाई एफ डी न्यू. And what is this? It is the same iterated integral whose existence we are assuming. वो सेकंड, ये सेकंड देखिए, assume this exists, ये वही iterated integral अब मिल रहा है आपको, यही मिल रहा है आपको नीचे. Now since we are assuming this exists, so that means it must be a finite quantity. इन्फिनिटी नहीं हो सकती बिकॉज एफ, माइनस इन्फिनिटी भी नहीं हो सकती बिकॉज एफ इज़ नॉन नेगेटिव, और प्लस इन्फिनिटी भी नहीं हो सकती बिकॉज वी आर अस्यूमिंग दैट दिस इटरेटेड इंटीग्रल एग्जिस्ट्स. डी म्यू है ये, सॉरी, ये वही इटरेटेड इंटीग्रल है जिसकी एग्जिस्टेंस हम अस्यूम करें. सो दिस इज लेस देन इन्फिनिटी, फुल स्टॉप. ठीक. Now we take a look at the information which we have at our disposal now. हमारे पास पहली information है कि that gamma n's are stub functions. They are increasing and they are stub functions over the product measure space because they are functions defined over the product measure space, and they are converging to f. So we have a sequence of stub functions. I have a sequence of stub functions which is increasing to f because gamma n's are increasing and converging to f. So that is the reason I am saying we have a sequence of stub functions which are increasing to f over the product space over x cross y. और हम नीचे देख रहे हैं ये जो stub functions हैं इनके जो integrals है over the product space, in the limit those integrals are finite. ये देखिए, these are integrals of these stub functions over the product space, and in the limit these integrals मैं आपको दिखा रहा हूँ, they are finite. And this means what? This means मैं यही लिख रहा हूँ, इसकी consequence क्या है? Consequently gamma n running from 1 to infinity is a what? Is a generating sequence. Is a generating sequence for f over the product space over x Cartesian product y s o times sigma. जो generating sequence के लिए होना चाहिए वो सारी चीज़ें fulfill हो रही है, mu cross nu. Full stop. Now that f has a generating sequence, so f becomes an upper function and consequently an integrable function because every upper function is integrable. Therefore, f is an upper function and hence an integrable function, and hence an integrable function. It has a generating sequence over the product space, so it's an upper function over the product space. Upper functions are integrable, so it is an integrable function over the product space. Hence an integrable function over the product space x Cartesian product y s o times sigma mu cross nu. Full stop. That proves the integrability, and now the rest of the proof follows by Fibonacci's theorem, because once the function is integrable you can use Fibonacci's theorem on f. Now f पे आप, because f is mu cross nu integrable, now I can use Fibonacci's theorem and I can conclude that both the iterated, a की तो मैं already assumption, a की existence तो मैं already assume कर रहा हूँ. Fibonacci's theorem will guarantee कि that other will also exist, and the iterated integrals and the joint integral, their double integral will be same. मैं यही लिख रहा हूँ. The rest of the proof follows by using Fibonacci's theorem. बस असल में यही है, to somehow show the integrability. वो हो गई. Now we can use Fibonacci's theorem to complete the proof. The rest of the proof proof. Rest of the कैसे लिखेंगे इसको? ठीक है, यही लिखे, rest of the proof now follows by using the Fibonacci theorem. This proves the Tonelli theorem completely. So I have proved this result. This is the proof. So in order to prove this, we basically show that this f is an upper function, जो ना strategy है यहाँ. और उसके लिए we made use of these lemmas. अब देख कैसे किया वो आपने देखा during the course of the proof. So this is Tonelli theorem. This is all about the Tonelli theorem. अब मैं आपसे क्विकली कुछ चीज़ें यहाँ डिस्कस करना चाहता हूँ about the structure of this collection of all possible measures defined on some sigma algebra of subsets of a non-empty set. पहले एक नया पेज स्टार्ट कर रहा हूँ. अब क्या करिए, अब ऐसे ना वो हो गया Tonelli theorem का, वो कंप्लीट हो गया वो डिस्कशन, और दिस इज अ न्यू डिस्कशन. अब इसके लिए यहाँ क्या करिए, लेट x बी अ नॉन एम्प्टी सेट, sigma, capital sigma, be a sigma algebra of subsets of x and m sub x of sigma, ऐसे लिखेंगे आप, and this be the collection of all possible measures. This will be the collection of all possible measures defined on the sigma algebra. ठीक है. अब जितने भी measures आप सोच सकते हैं on defined on this capital sigma, वो सारे आपने यहाँ लेने हैं. फिलहाल we are only taking measures, not signed measures. और signed measures के लिए हम जो collection है उसको कुछ different symbol assign करेंगे. This is simple m, by the way, m sub x of sigma. उसके लिए हम जो साइनड मेजर्स की कलेक्शन है उसके लिए हम स्क्रिप्ट m इस्तेमाल करेंगे. फिलहाल के लिए वी आर ओनली डीलिंग विद मेजर्स, नॉट साइनड मेजर्स, ये जहन में रखिएगा. अब आप क्या करिए, यू टेक टू मेजर्स इन दिस mx, पिक टू मेजर्स, म्यू कॉमन न्यू इन m sub x sigma. Now this is collection of all possible measures, then there will be measures on sigma actually. Then मैं ये लिख रहा हूँ आपकी अंडरस्टैंडिंग के लिए, then mu common nu are measures on this sigma algebra, capital sigma. ठीक है, full stop. अब हम क्या करेंगे यहाँ, you define something. I'll define something. Define इनिशियली मैं इसके लिए एक artificial symbol use karunga for what I am defining, and later on we'll switch to a more reasonable symbol. Initially I'll be using this symbol omega. Omega from capital sigma into 0 infinity. Basically this omega, which I am claiming to be a set function defined on capital sigma, I'll create this omega using this mu and nu. और कैसे वही मैं आपको बता रहा हूँ, by इसकी जो description है वो ये होगी. In order to compute omega at a, आपने क्या करना है, you need to do this. ये देखिए अभी क्या हो रहा है यहाँ. Pay careful attention to this. You need to evaluate mu at b. अब ये पूरी इंफॉर्मेशन नहीं है तो आपको थोड़ा सा वेट करना होगा. प्लस न्यू एट a minus b, such that b belongs to the capital sigma, belongs to the sigma algebra, and b is contained in a. I suggest to you to draw a picture for this, because अगर ऐसे आप खाली देखेंगे आपको कुछ समझ नहीं आएगा. So what is the situation here? वो ये यहाँ जो situation है वो ऐसी है कुछ. Suppose this is A और इसके अंदर एक territory है which is B. ठीक ऐसे. अब आप क्या कर रहे हैं, ये जो टेरिटरी है बी वाली टेरिटरी, इस पे आप बी वाली जो टेरिटरी है ये, इस पे आप म्यू अप्लाई कर रहे हैं. वी आर यूजिंग म्यू हेयर. और ये जो बाकी जो पोर्शन है बिटवीन ए एंड बी, मतलब इन ए आउटसाइड बी, उस पे हम जो है वो न्यू इस्तेमाल कर रहे हैं. यहाँ न्यू इस्तेमाल हो रहा है. एंड देन वी आर टेकिंग द सम. So in a way this sum in a way is a joint action of mu and nu on A. आप ऐसे समझ लीजिए mu and nu, they are two labors, and this A is some plot of land. mu जो है वो ये B टेरिटरी पे काम करता है और जो न्यू है वो बाकी टेरिटरी पे काम करता है. सो आपको नहीं लगता देन म्यू ऑफ बी प्लस न्यू ऑफ ए माइनस बी वुड बी द जॉइंट एक्शन ऑफ म्यू एंड न्यू ऑन दिस ए related to this b? You pick a b in capital sigma with b contained in a, and that b happens to be the share which goes to mu, and the remaining portion goes to nu. ठीक. So I can see this, I can interpret this as a joint action of mu and nu on A relative to this B. Because ये B ही decide करता है कि mu के हिस्से में कितना जाएगा और nu के हिस्से में. That is the reason I am saying relative to this B. And clearly if I change this B, the joint action will change. If I change B, B is the share which goes to mu. Or if I change B, obviously यहाँ सारी equation ही बिगड़ जाएगी. So everything depends upon B. Basically the sum depends upon B. So basically for each B in the sigma algebra with B contained in A, we can think of a sum for each such B. And if you collect all these sums, for each B there is a sum. We have to collect all these sums, and in this way we'll get a set of these sums, and we eventually take the sup of that set. The sup of this set is what omega A will be. So omega A will be actually the sup of this set. ठीक है. तो दिस विल बी ओमेगा ऑफ ए. एंड लाइकवाइज अब यहाँ आप सुप ले रहे हैं, ओमेगा ए इज इक्वल टू दिस फॉर ऑल एस इन सिग्मा. अब जिस तरह से आप यहाँ ना ये सुप ले रहे हैं, इसी तरह से आप इन्फ भी ले सकते थे, इन्फिमम, राइट. आप इन्फिमम का भी इस्तेमाल यहाँ कर सकते थे. तो अगर आपने किया होता तो बेसिकली वहाँ से आपको एक नया फंक्शन मिलता, वो कोई डिफरेंट फंक्शन होता. फिलहाल सुप वाले फंक्शन को हम ओमेगा से डिनोट कर रहे हैं. आपके लिए एक्सरसाइज ये है कि यू नीड टू शो दिस ओमेगा इज एक्चुअली अ फंक्शन. दिस इज एन एक्सरसाइज फॉर यू. शो दैट मैंने क्या कहा था, ओमेगा इज अ, नहीं, आई शुड से ओमेगा इज अ मेजर. मुझे लग रहा है शायद मैंने ना आपसे कहा कि ओमेगा इज अ फंक्शन. वो तो है, आपको दिखाना है कि ओमेगा इज अ मेजर. दिस इज एन एक्सरसाइज फॉर यू. शो दैट दिस ओमेगा, जिसको हम इस तरह से डिफाइन कर रहे हैं, ओमेगा इज अ मेजर ऑन कैपिटल सिग्मा. ठीक. The verification is easy. You can easily show that this is indeed a measure on capital sigma. So basically the moral of the story is, using these two measures, mu and nu, we can create another measure, omega. और omega में आप basically क्या करते हैं, you in a way take the supremum of the all possible joint actions. मतलब जो सबसे बड़ा joint action है ना mu और nu का, वो आप लेते हैं, sup. इसी तरह you can also speak about the inf of. और अगर आप ऐसा करेंगे, it turns out that the inf is also a measure. और ये भी मैं आपके लिए छोड़ रहा हूँ. Further, if pi is used here as a symbol, not as the constant pi, which is the ratio of the circumference and the diameter. ये वो नहीं है. This is just a symbol here. Further, if pi from capital sigma into 0 infinity be defined as like this. इसके लिए हम क्या करेंगे, फिर से वही, in order to compute pi at a, where a is coming from the sigma algebra, हम क्या करेंगे, we'll first consider the set of all possible joint actions. That means mu of b plus nu of a minus b, such that b is coming from the sigma algebra and b is contained in a. This will be the set of all possible joint actions of mu and nu on a. और हम क्या करेंगे, हम इस सेट का इन्फ लेंगे, और जो ये इन्फ है इसी को हम डिफाइन करेंगे एज pi of a. So pi of a जो है ना, in a way targets the smallest joint action, and you can again show that this pi is also a measure. Then this pi is also a measure on capital sigma. ठीक है. So we have created two measures, omega and this pi. Now I want to test the relationship between. Obviously we are creating, since we are creating omega using mu and nu, so we expect that this omega, it should be related to mu and nu. Likewise, since we are creating this pi using mu and nu, so we expect that there should be a relationship between this pi and these two measures, mu and nu. ठीक है. और ये रिलेशन देखना भी कोई डिफिकल्ट काम नहीं, इट्स इजी. देखिए कैसे आप इसको चेक करेंगे. आप क्या करिए, you take mu of a. Now mu of a I can write as mu of a plus nu of a minus a. लिख सकते हैं ऐसे इसको, because a minus a will be phi, so this will be nu of phi. Nu of phi is 0, so this is mu of a plus 0 means mu of a. So mu of a को ऐसे लिखा जा सकता है. ठीक. Now what I can do here, I can see this a as b now. I can see this a as b. I can see this as mu of b प्लस न्यू ऑफ, ना यहाँ दो कॉपीज है ए की, ये वाली कॉपी को ए ही रखेंगे, ये वाली कॉपी को हम देखेंगे एज बी. सो इसको ऐसे लिखा जा सकता है म्यू ऑफ बी प्लस न्यू ऑफ ए माइनस बी. और मैं यहाँ आपको बता रहा हूँ वेयर दिस बी इज इक्वल टू ए. ठीक, और चूंकि ए पर आप म्यू अप्लाई कर रहे हैं, राइट, so A must be coming from the sigma algebra, so B is coming from sigma algebra, and since B is equal to A, so B can be seen as a subset of A also. ठीक, so B is coming from sigma algebra and B is a subset of A, so that means this can be seen as the joint action, and this is equal to this, so this can be seen as the joint action. ठीक है, now omega is the supremum of all the joint actions, so therefore this must be less or equal to omega of A. So the information that is coming out of this, coming out of these arguments is this: mu of A is less than or equal to omega of A, and this is true for which A's? The answer is it's true for all the A's in capital sigma. So mu of A is less or equal to omega A for all the A's in capital sigma. Likewise, we can also see that nu of A is also less or equal to omega of A. मैं आपको detail दिखा रहा हूँ कैसे. If you take nu of A I can write as mu of phi plus nu of A. लिख सकते हैं? Now I can write this as mu of B if I take phi as if I take B as phi plus nu of A को लिखा जा सकता है as nu of A minus B, where B is equal to phi, the empty set. If you take B as the empty set, आप देख सकते हैं this is actually nu of A. तो ये किया जा सकता है. ठीक, now empty set is coming from the sigma algebra, so B is coming from sigma algebra and B is phi, so B is subset of A. So again I can see this as a joint action of mu and nu on A. ठीक, and since omega is the sup of all the joint actions, so this must be less than or equal to omega of A. So nu of A is also less or equal to omega of A. So that means both mu and nu, they are less or equal to omega. ठीक है, तो इन्फॉर्मेशन यहाँ से निकल के आ रही है. न्यू ऑफ ए इज लेस और इक्वल टू ओमेगा ऑफ ए, एंड दिस इज ट्रू फॉर ऑल द एज इन कैपिटल सिग्मा. सो दैट मीन्स व्हाट? दैट मीन्स this measure omega is an upper bound for mu and nu. So thus this omega is an upper bound for mu and nu. It's an upper bound. ठीक. Now if omega 1 be some other upper bound, some other upper bound for mu and nu, then हम देखना चाहते हैं कि how this omega 1, which is some other upper bound of mu and nu, how this omega 1 is related to this omega. Omega we already know it's an upper bound. Now I'm taking another upper bound, possibly some other upper bound, omega 1, and now I want to test its relation with this upper bound omega. और ये कोई ज़्यादा मुश्किल काम नहीं है. आप उसके लिए क्या करिए, you take a joint action. आप क्या करिए, you take A in capital sigma, B in capital sigma with B contained in A. राइट, ऐसा करें आप. फिर इसके बाद आप इसे लीजिए, you take mu of B plus nu of A minus B. आप चाहे तो यहाँ फिर से एक पिक्चर ड्रा कर सकते हैं. सपोज दिस इज A और इसके अंदर है B, and they are all measurable sets because they are coming from the sigma algebra. So A, B and this ring shaped territory, which is actually A intersected with B complement, this will also be measurable. So measurability is not an issue. Now first we'll use this. We know that omega 1 is some other upper bound, means it's an upper bound for mu and nu. So mu of b will be less than or equal to omega 1 of b. ठीक, and likewise nu of this will be less than or equal to omega 1 of this, because omega 1 दोनों का upper bound है. So this plus 1, this will be less or equal to omega 1 of b plus omega 1 of a minus b. Now omega 1 of b plus omega 1 of a minus b, ये picture से आप देख सकते हैं. a minus b means the ring shaped region and this is b, तो दोनों पे आप omega 1 इस्तेमाल कर रहे हैं. These are disjoint and measurable, so and omega 1 जो है, we know that it's a measure, it's an upper bound for mu and nu. So क्या होगा, this is equal to, using the additivity of omega 1, this will be equal to, अब यहाँ लिखेंगे be some other upper bound of mu and nu in, मुझे बताना चाहिए कि ये कहाँ से आ रहा है, m sub x sigma. That means this omega 1 is a measure and it also dominates mu and nu. Now you can use the additivity and you can see that this is equal to omega 1 of a. So basically मैं आपको दिखा रहा हूँ that omega 1 of a, it dominates all the joint actions, because we know that a joint action on a is actually governed by b. यहाँ b कोई भी b हो सकता है of a, subset of a. So basically मैं आपको दिखा रहा हूँ कि that this omega 1, it dominates every joint action of mu and nu on a. So if it dominates every joint action, so it must be an upper bound for the set of joint actions. Omega 1 must be an upper bound. So it must be greater or equal to the sup of the set of joint actions, because sup of the set of joint actions is actually the least upper bound of the set of joint actions. ठीक है, तो यहाँ से जो निकल रहा है वो मैं थोड़ा केयरफुली लिख रहा हूँ. This shows that omega 1 of a is an upper bound, of the set mu of b plus nu of a minus b, where b is coming from sigma algebra and b is contained in a. So it's an upper bound of this. Now that it's an upper bound, so it must be greater or equal to the least upper bound, which is sup. Consequently, omega 1 of a, because it's an upper bound, so it must be greater or equal to this least upper bound, means the sup mu of b plus nu of a minus b, such that b varies over sigma algebra and b is contained in a. And what is this sup? This sup is actually omega of a. ठीक, so that means omega 1, this is true for which a's? The answer is true. It's true for all the a's in sigma. That is, this omega 1 measure, it dominates measure omega. That is, sorry. तो क्या दिखा रहा हूँ मैं आपको दिखा रहा हूँ कि that omega is an upper bound for mu and nu, and if omega 1 is some other upper bound of mu and nu, then omega 1, it dominates omega. That means this omega is dominated by every other upper bound. तो यहाँ जो information है वो ये है, एक तो ये omega खुद एक upper bound है, and it is dominated by every other upper bound. So that means it is the least of the upper bounds. So that means this omega is actually the sup of these two measures. So the moral of the story is, given two measures in mx sigma, mu and nu, I can also speak about their sup, जिसको हम lattice terminology में join कहते हैं. So I can speak about mu join nu, और ये mu join nu क्या होगा? It will be actually precisely जिसको हमने omega कहा था. And what is this omega? वो उसकी description. क्या है वो आपको पता है, इट इज़ द सुप. सो वी कैन स्पीक अबाउट दिस. लाइकवाइज जो वो पाई आपने देखा ना, जो मैंने आपके लिए रखा था कि दैट इट्स अ मेजर, इसकी वेरिफिकेशन. दिस पाई इज एक्चुअली अ लोअर बाउंड फॉर म्यू एंड न्यू. मतलब it is dominated by mu and nu, and this pi, it dominates every other lower bound for mu and nu. So this pi is actually the greatest lower bound of mu and nu. So that means it's actually the infimum. So that means we can also speak about the infimum. और lattice terminology में हम infimum को meet से denote करते हैं. So that the moral of the story is this: if you have mu and nu in mx sigma, you can all speak about the join as well as the meet. ठीक, और इनकी डेफिनेशंस क्या है मैं बस वो लिख रहा हूँ, एंड उसके बाद आप जा सकते हैं. फॉर म्यू कॉमन न्यू, मैं नया पेज स्टार्ट कर रहा हूँ, थोड़ा सा लैग हो रहा है मुझे इसमें अब. For mu common nu in this mx sigma, we define the join mu join nu at A. उनको कैसे डिफाइन करते हैं इसको, या मैं ठीक से लिखूँगा. we define this mu join nu from capital sigma into 0 infinity by the following rule. और वो रूल ये है, अब वही जो आप अभी देख रहे थे ओमेगा में, वही है रूल यहाँ. म्यू join nu when evaluated at A is defined as supremum of all possible joint actions mu of B plus nu of A minus B. अगर आप जिस तरह से मैं कह रहा हूँ, अगर आप इस तरह से इसको नहीं देखेंगे तो आपको थोड़ी सी प्रॉब्लम यहाँ आ सकती है, बिकॉज ना कुछ समझ नहीं आता यहाँ कि असल में क्या हो रहा है. इसको देखने का बेस्ट तरीका यही है, सी दिस एज अ जॉइंट एक्शन ऑफ म्यू एंड न्यू ऑन ए such that B is coming from capital sigma and B is contained in A. The sup of this set is defined as the join of mu and nu evaluated at A, and this is defined for all A's in sigma. So this is how we define the join. So likewise, we define, और ये डिफाइन करने का एक कंक्रीट रीज़न है कि मैंने आपको दिखाया इंडीड दिस इज़ एक्चुअली लीस्ट अपर बाउंड ऑफ म्यू एंड न्यू, जिसको हम लैटिस टर्मिनोलॉजी में ऐसे डिनोट कर सकते हैं फिर, बिकॉज इट्स लीस्ट अपर बाउंड, सो इट्स द जॉइन इन लैटिस टर्मिनोलॉजी. सो लाइकवाइज वी डिफाइन द मीट म्यू meet nu from capital sigma into 0 infinity by the following rule. Mu meet nu when evaluated at A, this is defined as the infimum of the set of all possible joint actions of mu and nu on A. That means infimum of mu of B plus nu of A minus B, where B is coming from sigma algebra and B is a subset of A. और ये हम करेंगे for all the A's in capital sigma. ठीक, ये वही है जो ओमेगा है ये असल में, और वो नीचे वाला जो वो पाई है, और दोनों मेजर्स हैं. So basically the meet and the join and the meet of two measures are again measures. The sup and the inf, least upper bound and greatest lower bound of two measures, is again a measure. So that means this mx sigma is closed under these two operations. It's closed under join and meet, because join is again a measure and meet is again a measure. So this mx sigma is closed under these two operations. Mx sigma is closed under these two operations, which we are denoting by join and meet. So that means this mx sigma is actually a lattice. Lattice होने के लिए यही चाहिए होता है. Thus, so collection of measures defined on a common sigma algebra is a lattice. Thus, the collection of mx sigma is actually collection of all possible measures. मैं ये लिख रहा हूँ, collection of all possible measures. फिलहाल हम खाली measures ले रहे हैं. Measures defined on a common sigma algebra is a lattice, because it's closed under these two lattice operations. So it's a lattice. In fact, it's a Banach lattice. वो हालांकि उसके लिए कुछ और टर्मिनोलॉजी चाहिए मुझे अभी, बट यह है कि फ़िलहाल के लिए आप ये दिखा सकते हैं इट्स अ कंप्लीट लैटिस. बट एनीवे आई लीव दैट. फ़िलहाल के लिए हम वो चीज़ नहीं देख रहे. तो फ़िलहाल आप यही चीज़ याद रखेंगे कि दैट इट्स अ लैटिस, बिकॉज इसमें अभी एक डेफिशिएंसी है. वो ये है कि दैट दिस mx sigma is not a vector space. Although it's closed under addition, sum of two measures is a measure. बट वो हमने परसों देखा, difference is not a measure, is not always a measure. So that could be a spoiler. In fact, that is a spoiler generally speaking. तो वो भी मैं आपको दिखाऊंगा उसको हम कैसे एड्रेस करेंगे. फ़िलहाल के लिए इतना याद रखिएगा. If you consider mx sigma and if you define using mu and nu, if you define this, if you use this as description of a set function, then this set function is a measure, and this measure is actually supremum, LUB of mu and nu. That is the reason we denote this by mu join nu. Similarly, if you consider two measures mu and nu, and if you define a set function using this description, if you define a set function on sigma, because A is coming from sigma, if you define a set function on sigma using this description, then this set function is again a measure, and this measure is actually infimum of mu and nu. And it is for this reason we are denoting this by mu meet nu. So in mx sigma we can take join as well as meet, so therefore mx sigma is a lattice. Mx sigma is the collection of all possible measures defined on the common sigma algebra, capital sigma. So conclude this: the collection of all possible measures defined on a common sigma algebra is a lattice.